Welcome to today's Explainer, where we're embarking on a high-stakes journey right into the heart of Cambridge IGCSE additional mathematics, specifically syllabus code 0606. Think of the exam hall like a Formula One racetrack. Every single second counts, and your mathematical strategy needs to be as precise as a pit crew. Today, we are mastering two-dimensional vectors. If you've ever found yourself wondering exactly how air traffic controllers prevent mid-air collisions, or how ship captains navigate the vast, featureless oceans without getting lost, the answer lies entirely in the mathematical tools we are about to decode. We're going to build our understanding systematically from the absolute ground up. We'll move rapidly from basic principles straight into solving complex, real-world interception problems that you'll face on your actual papers. No fluff, just pure, mark-scoring strategy.
Okay, let's kick things off with this beautiful quote from the source material. Thought is an idea in transit. This ancient wisdom from Pythagoras perfectly sets up our exploration today, because at its very core, vector mathematics is entirely about things in transit. It's the mathematics of movement, of direction, and of purpose. When you're sitting in that exam, your thoughts need to be directed and moving logically toward the final answer, much like the vectors we're about to study.
Here is our roadmap for today's session. We'll decode the essential terminology, visualize vector operations, apply them to real-world navigation, and finally, we'll master an actual past paper interception question.
Section 1. Decoding vector terminology. Before we can solve the complex problems, we have to make sure we're speaking the language fluently.
So, let's start with the absolute basics, and I need you to lock this into your memory. The crucial point here is that a vector isn't just a measurement of how much. It is intimately tied to where it's going. A vector is a quantity that must have both magnitude, which is its size or its length, and a specific direction. You literally cannot have a vector without both of these elements working together in perfect harmony. In an exam, if you only calculate the size but forget to define the direction, you are throwing away incredibly easy marks.
This perfectly illustrates the crucial difference between a scalar and a vector. A scalar is literally just a number with a unit attached to it. For example, a speed of 60 kilometers per hour. It tells you exactly how fast an object is moving, but it gives you absolutely no clue where it's going. It could be going up, down, left, right, we don't know. But the very second you add a strict direction to that number, like saying it's moving 60 kilometers per hour directly south, that basic speed transforms into a velocity, and velocity is a vector. This distinction is the bedrock of everything we're going to cover today.
As you review your source materials and dig into your past exam papers, you are going to see vectors written in several different ways. You need to be completely comfortable recognizing all of them instantly so you don't waste precious time in the exam. In print, vectors are usually bolded. Now, when you write them by hand on your exam paper, you absolutely should underline them. If a vector joins two specific points, like from an origin to a point A, you'll see a small arrow drawn above the letters OA. You'll also frequently encounter column vectors, which have an x component stacked cleanly on top of a y component, or the standard INJ unit vector notation. Keep a sharp eye out for these conventions. Now, before we continue, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGC to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Section 2. Visualizing vector operations. Now that we know how to identify them, let's look at how we actually manipulate these vectors mathematically.
Adding vectors in component form is incredibly straightforward. It's almost impossible to mess up if you stay organized. You just add your x components together, and then you separately add your y components together to get your final resultant vector. Now, subtraction can sometimes trip students up, especially when they rush, but it's just as easy if you mentally reframe it. Subtracting one vector from another is really simply adding its equivalent negative vector. Thinking of subtraction this way makes it an absolute breeze. It prevents those silly sign errors that inevitably happen when the pressure is on and the clock is ticking down. This leads us naturally to a fascinating yet incredibly important concept, the zero vector. Imagine this scenario. If you add a vector to its exact negative counterpart, meaning you travel a certain distance in one specific direction, and then you turn around and travel the exact same distance in the direct opposite direction, you arrive right back exactly where you started. Your net movement is nothing. This gives us the zero vector, which is quite literally a vector with zero magnitude.
What's really interesting about this slide is how Pythagoras' ancient theorem from literally thousands of years ago is the direct mathematical key to finding what we call a unit vector. A unit vector is incredibly useful. It's simply any vector that has a length or magnitude of exactly 1. To find it, you just follow these steps. First, take your standard vector and identify its components. Second, use Pythagoras' theorem on those x and y components to calculate the vector's total length. Finally, you take the original vector and divide it by that length. What this does is scale the entire vector down until it's exactly 1 unit long without altering its path even a single degree.
And speaking of scaling vectors, we absolutely need to touch on scalar multiplication. Remember from earlier, a scalar is just a regular number, a magnitude without a direction. When you multiply a vector by a scalar, all you are doing is stretching or shrinking the line. If you multiply a vector by 3, it becomes 3 times as long. If you multiply it by a half, it shrinks to half its size. But the absolutely crucial takeaway here, the thing examiners want to see you understand, is that its direction remains entirely unchanged. It is still pointing the exact same way, it's just reaching further or shorter. Stop scrolling, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Section 3. Real-World Vector Navigation. This is where we step out of the abstract formulas and apply these rules to the real world, where actual movement happens.
Our source material highlights how vectors aren't just dry classroom concepts. They are quite literally the backbone of real-world navigation and meteorology. Have you ever looked at a complex weather map showing wind patterns? Those arrows you see are vectors. They indicate not just how intensely the wind is blowing, the magnitude, but the precise direction it's traveling across the surface of the Earth. Without vectors, modern navigation would be completely impossible.
Let's look at a brilliant, highly practical example from the text, featuring 2 sailing boats out on the water, the Antares and the Bellatrix. Notice how we can seamlessly translate a boat's real-world compass bearing and speed into exact I and J mathematical components. Look at the Antares. It's moving at a speed of 3 kilometers per hour on a true bearing of 30 degrees. By using basic trigonometry, specifically our good friends sine and cosine, we can easily break that physical angled path into a horizontal and vertical mathematical component. It becomes the vector 1.5i plus 2.6j. Now look at the Bellatrix. It's doing 2.5 kilometers an hour at a bearing of 127 degrees. Through the same process, that translates to the vector 2i minus 1.5j. We've successfully turned physical, real-world motion into pure workable math.
So why does translating movement into I and J components actually matter? Because by following these logical steps on the slide, we can track exactly how far apart these 2 boats are out on the open ocean after 2 whole hours of sailing. First, we use the scalar multiplication we learned earlier, multiplying their hourly velocity vectors by the scalar of 2 hours. This gives us their new positions. Then, we subtract the Bellatrix's position vector from the Antares position vector to find the relative displacement vector between them. Finally, we unleash Pythagoras on that resulting displacement vector, which is minus 1i plus 8.2j. Calculating the magnitude gives us a final distance of 8.3 kilometers. They are exactly 8.3 kilometers apart. This is the true power of vector math, pinpoint accuracy from just a few variables.
Section 4. Mastering Exam Questions. Let's take all this theory, put on our strategist hats, and decode an actual Cambridge past paper question together. All right, focus in, because this is a classic high-stakes exam scenario from the June 2014 0606 paper. This strictly tests your ability to mathematically model a moving interception under time pressure. We have a target ship cruising across the ocean, and a speedboat leaves a stationary lighthouse with one single mission: intercept that ship. We need to find out exactly what time they collide. This is where students who rush completely fall apart, but if you apply our systematic strategy, you'll secure every single mark.
To solve this correctly, we must carefully contrast their starting variables. I see students miss this constantly because they don't read the data properly. The target ship leaves its origin port at exactly 12 hours. However, the intercepting speedboat doesn't leave the lighthouse until 1600 hours. That means the target ship has a massive 4-hour head start before the speedboat even fires up its engines. If you don't account for that time difference, your entire calculation is immediately wrong. Furthermore,
Notice that the lighthouse isn't at the origin 0, 0. It has its very own starting position vector of 120i plus 81j. You have to matrix all of this data before you even think about writing an equation.
The absolute secret to solving this lies in expressing both of these moving vessels as complete position vectors, relative to an unknown variable of time, which we'll call t. By doing this, we create two distinct mathematical paths. Because an interception means they absolutely must be in the exact same physical place at the exact same time, we simply take those two position vectors and set them equal to each other. You equate the I components, you equate the j components, and suddenly, this highly complex maritime chase sequence becomes a deeply satisfying, easily solvable algebraic equation. Find t, and you've found your exact time of interception. It's brilliant!
As we wrap up the core content of this explainer, I need you to commit this success blueprint to memory. Always, always be clear on the difference between a scalar and a vector in your definitions. Remember that Pythagoras is your absolute best friend when calculating magnitude or distance. Never forget that position vectors always originate from 0, 0. And finally, rigorously practice converting physical compass bearings into mathematical I and j component form using trigonometry. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE to excel in your Cambridge examinations. Subscribe right now to @Ace the Exams IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams, your Cambridge success starts here.
Just think about that for a second. You've just seen firsthand how a handful of elegant, logical mathematical formulas can literally pinpoint two isolated objects moving independently across the vastness of the ocean. It's incredibly powerful. I'll leave you to ponder just how potent these mathematical tools truly are when applied to the chaotic, constantly moving world around us. What else could you track with vectors? What else could you accurately predict? The applications are endless. Keep practicing your math, keep refining your exam strategies, and I will see you in the next session.